I've had a few comments about whether I was planning on doing any DSP or digital signal processing versions of the circuits that I've been putting together, the phase shift network, the filters, and so on and so forth. So it has actually been a dream of mine to build a MicroPython-based software-defined radio on one of the ARM platforms. I haven't quite gotten around to that, but what I thought I'd show is what's possible using the board that you can see right there, the Teensy. What you're looking at here is the Teensy 4.0 with the associated audio shield. So the Teensy's on the top there, and you can see it runs, this is an ARM M7 processor at 600 megahertz, so there's more than enough power in that to run DSP. But the additional thing that's provided on the Teensy site, and I'll provide a link to that below, is what you can just barely see underneath it. This is a kind of fully functional audio shield that allows both audio in, stereo audio in, as well as line out. There's a place for a microphone there, and it has an audio processor built onto the board that communicates to the Teensy over the I2C protocol. So the other good thing that comes with the Teensy is there is a huge audio library that's been developed to take advantage of all this, and it comes with a variety of finite impulse response filters, mixers, Fourier analysis, and so on and so forth. So it's a really good set of software. Now that's all provided for the Arduino sort of programming environment. I'd love to be able to do the same thing on my MicroPython, one of my MicroPython boards. But what I thought I'd do is just walk through in this video some of the things that you can do with the Teensy. So I'll show the basic setup, how the Teensy connects to the audio shield, a little simple program that shows I send a signal in and I can receive a signal out. Then I'll move on to how to develop a 90-degree phase shift using a pair of finite impulse response filters and some software that comes from a site called Iowa Hills that allows you to define that. And then finally what I thought I'd do is I'll hook all of that up to one of those double balance mixers that I produced in one of the previous videos, and we'll be able to sort of compare and contrast how is the performance of the Teensy and its in-software 90-degree filter compared to the op-amp filters that I've been using. So anyway, more to come. Let's go through some basic setup. So when you first get your Teensy and the audio shield, they come as two separate boards. So none of this is connected together. I don't even know if you can actually order it with these two soldered. So here's the top board is the Teensy, the bottom board is the audio shield. So the way you connect those two together is you use some of these long 14-pin headers, and then as you can see, the header goes all the way through, connecting those two boards together. Now note the orientation here. So the USB connector of the Teensy is on the opposite side of the board from the SD card of the audio shield. So you've got to make sure you get that orientation right. Certainly before you do any soldering at all. So also note that the board does come with a stereo output jack, but if you want to send signals to your audio shield, you have to connect a stereo jack. That's what got one right here, to these two rightmost innermost connections right here and here. So this is input, and then there's a further line out right here, and this is just a convenient ground that I've got here. So finally, there's a place spot for an electret microphone right here. If you wish it, you can solder that in place. So note the orientation there. Electrets are polarized. Here's the ground, and here's the signal. So now that we've set up the Teensy, let's just go through a simple example where we configure the Teensy in a pass-through mode. And I've got that right here in the Arduino code. So here I've specified an input, an output, and then there's a simple patch cord between the inputs and the outputs. So basically this just routes anything that's seen on the left and right channels of the input to the output. So I flashed that code into the Teensy, and just to describe the setup here, here's line out, so this is going off to my speakers. Here's line in, and that's coming from the signal generator. Just pan up so you can see that. So I've got the signal generator set at 1 kilohertz, half a volt peak to peak. Let me just enable that, and you'll be able to hear the speaker. So there's the signal coming from the signal generator through the Teensy, doing some pass through, and then out through the line out. So obviously, as I adjust the frequency of the signal, so now we get to the whole subject of digital signal processing and finite impulse response filters, and I'm not really equipped to talk to that from a theoretical perspective. I don't know the theory, it involves complex math, and I've included some links below to that for those who are interested. However, from a practical perspective, it's a little easier to understand. The filter takes a stream of data, let's say from an ADC, and applies a convolution operation against that data with a series of coefficients that's created through filter design software. So typically the convolution algorithm is handled in one of the core libraries. So in the case of ARM filters, usually the CMSIS ARM libraries handle the convolution operation. And what results out the other side is a stream of digitized output that you send out through the digital to analog converter, and then you get a modified waveform. So basically the flow is you have an input waveform, passes through the finite impulse response filter, and that filter is configured through coefficients, and that defines how the filter behaves: low pass filter, high pass filter, band pass filter, and then finally the digitized output is passed to the digital analog converter out of the other side. So this list of coefficients, also known as the impulse response, is a one-dimensional array of either integers or floating point numbers, depending on the library that you're using. And the number of coefficients in that is generally referred to as the number of taps. So the values in the array determine the operation, as I mentioned before: low pass filter, high pass filter, and so on and so forth. Now the trick is, well, how do I derive those coefficients? So typically external filter design software is used to do that. So I'll take you through some examples here from a website that I'll provide a link below called Iowa Hills, but you can also design this software using, for Python, it's SciPy, their equivalent libraries in C and so forth. Okay, so let's get back to the problem that we're trying to solve here, and basically that's this here, is what I want to do is take an audio signal, ingest that into the Teensy, and then split that audio signal into two components, so exactly the same components but shifted 90 degrees out of phase with respect to one another. So to achieve that, we use the Hilbert filter, which is a special case of a bandpass filter, where passing the signal through two independent Hilbert FIR filters generates a defined phase offset between the two signals. So I've defined here a plus 45 Hilbert filter and a minus 45 Hilbert filter, the result of which is that those two signals are out of phase with one another by 90 degrees. Now, obviously the challenge is, so how do I generate the coefficients? And that's where the Iowa Hills software comes in. So let's quickly go through creating the filter coefficients using the Iowa Hills software. And I've actually got it running on my Linux laptop here. It is actually Windows software, so you have to run Wine or something like some kind of Windows emulator to run it. And I'll include a link below to the Iowa Hills website itself. So let's just go through some of the setup here. So the goal is to produce two sets of coefficients, one at plus 45 degrees, one at minus 45 degrees. So let's just go through some of the settings here. So firstly, you want to select, bear with me here. Firstly, you want to select in the pass band a phase added type of filter. Sorry, I selected mixed there. Let's go back to phase added. Okay, so the next thing you want to do is put in the sampling frequency. So obviously this will vary depending on the processor you're using. The Teensy happens to sample at 44.117 kilohertz. Then you pick the center frequency of the bandpass filter and the bandwidth of the filter itself. So ideally you want the center frequency down low, at least for the audio filters we're looking at. So this is specified in terms of the Nyquist frequency, which is half the sampling frequency. So let's say I want to do 0.2 of that. That results in 4 kilohertz. That's still a little bit high. I want to probably around 2 kilohertz. So let's go down a bit lower. Bear with me. All right. So now I'm down at 2.21 kilohertz, and then the bandwidth of the filter itself. Let's say I want about an 11 kilohertz bandwidth there. For some reason that's not updating. Then you select the number of taps. So the number of taps is essentially the number of coefficients that you're generating. The more taps, the better the performance of the filter itself, but the more computationally intense it is. On the Teensy, you can have up to 200 taps. So that's 200 independent coefficients for the plus 45 filter, and a similar 200 coefficients for the minus 45 filter. And then finally, you want to check this little checkbox here, and that produces on the left-hand side of the screen, which is kind of scaled incorrectly. That's one of Wine's little challenges, is it has a hard time sometimes scaling Windows programs. But here's the 160 coefficients down here. Now these coefficients, when you send them to the Teensy doesn't deal with floating point numbers in its FIR filters. It deals with numbers between 0 and 32768. So you have to do some normalization on those numbers, and I'll show you that right next. So here's the Arduino software here before. I've modified this a little bit to add the SI5351 here, because I want to actually use a double balance mixer to see the effect of this. But so this setup is from before, where I have the basically I define an audio input and audio output. I've defined 2 FIR filters, one to do the plus 45 Hilbert transform, one to do the minus 45 Hilbert transform. And then I use this patch cord to hook them up. So you can see here, channel 0 of I2S1, the input, goes to channel 0 of FIR1. Channel 1 of the input goes to input 0 on FIR2. And then FIR2 goes to channel 1 of the output, and FIR1 goes to channel 0 of the output. So just scrolling down to the coefficients themselves, so you can see here, these are directly the values from the Iowa Hills software. So there's 160 values there corresponding to the 160 taps on the filter. And then I have the plus 45 coefficients, another 160 coefficients there corresponding to the 160 taps. And then the first thing that I have to do is transform those coefficients into what the Teensy wants, and the Teensy wants short integers. So I basically do a simple transform there where I iterate through the floating point, the double on the input, and I multiply each element by 32768. And that gives me a short int version, which is what the Teensy filters require. So just to round out the description of the code, the setup is very simple. You can see here, you've seen this software before, that just initializes the SI5351. There's the transform coefficients call for the coefficients from the IR Hills, and then these are the integers that go to the Teensy. And then simply, this is the setup for the Teensy audio library itself. So you just enable the control set your select line in as your input, and then you kick off the FIR filters. So at this point in the code, the sampling, the processing, and the output through the DAC, that's all happening as soon as you execute that code. So I've kicked off that code, so let's have a look at the setup over here, and then we can see what the output. So it's a bit of a rat's nest of wires here, but let me try and go through this here. So I've got my signal generator up the top here. It's currently outputting a 1 kilohertz signal at half a volt peak to peak. I'm sending that signal directly into the line in for the Teensy, so that's coming in here. And then on the output side, on the left and right channels, I've got the left channel hooked up to oscilloscope trace 1 and the right channel hooked up to oscilloscope trace 2. So what we should see on the oscilloscope is that those two signals are now 90 degrees out of phase with one another. So let's just pan up and confirm that. So there you can see those two signals are indeed 90 degrees out of phase one another. So we can drill in a little bit and do some rough calculations. Again, it's always a bit of a challenge, but so basically this is a half wavelength here. So 1, 2, 3, 4, 5, roughly 5 divisions there, and you can see between here and here is roughly 2.5 divisions. So that's an eyeball way of verifying that they're 90 degrees out of phase with one another. So let's change the frequency and see what happens at higher frequencies. So let's just go up, and you can see that phase relationship is being maintained there. So as you can see here, it's a little bit harder to see here, but so between here and here we've got 1, 2, 3.5, and roughly, I mean, it's hard to eyeball this, but you can see that phase relationship's maintained across frequency. So now I'm up at let's say 4 kilohertz. You can see there that phase relationship's maintained. Now, one of the challenges with the Hilbert filters is as you go down in frequency, and let's go down to back down to 1 kilohertz, and then we'll start going down from there. I'll just decrease the time base there. You can see that as I go down, that phase relationship is starting to get worse and worse. So now we're down at 300 hertz, and you can see these two signals are no longer 90 degrees out of phase with one another. And you can actually see that on the Iowa Hills software itself as it simulates that. Let me just pan up there and get the Iowa Hills software back online. So you can see here, this blue line is the phase. So you can see it at lower frequencies. So we're down here at roughly 300 hertz. That phase relationship starts to deviate from the 45 degrees that we want. So we got 45 degrees roughly here. Down here, you can see that phase relationship starts to change. So down low, below, so let's say 400 hertz, that filter is no longer performing its job. So the final test I want to do is put the left and right 90 degree out of phase output through that one of those double balance mixers that I created before. So this is the ADE 10L based double balance mixer that I used before. And again, just to remind you what's going on here. So these two channels here are the LO signals that are coming from the SI5351 at 90 degrees out of phase with one another. So that's just controlled by the Teensy, and I've just got that hard-coded to 7 megahertz for the moment. So they're going into here and here, the LO signals. This is where I'm tapping the output, and that's going off to the signal analyzer. And then this stereo signal here, the left channel contains the 0 degrees and the right channel contains the 90 degrees signal from the Teensy. So let's look up at the spectrum analyzer and see what we can see there. So as you can see there, that's that very nice, here's the upper sideband, and here's the lower sideband, and here's the carrier frequency. Now, the lower sideband suppression isn't that great. You can see that's minus 17 dBm, and the lower sideband is minus 42 dBm. So that's about 25, 26 dBs of suppression there for the lower sideband. The other thing to note, though, is all those messy harmonics that I had before using the op-amp-based phase shifters are basically not present at all here. And even if I expand the span outwards, let's go to 100 kilohertz span here, you can see that all of that mess that was on the op-amp-based phase shifters is gone. So again, I've got to do some experimentation with those op-amp filters. I was using very cheap components there, so that could be the cause of it. There's a variety of different things going on. One other thing, I did order some 1% capacitors for the phase shifter. I was using 5% before, so maybe that'll make a difference. I'll do an update video later on if it makes a difference. Let's just go back to a span of 20 kilohertz here for a bit. And through the Arduino software, what I'll do is I will swap those filters around. And what you should see when I do that is that the upper and lower sidebands are swapped around. So bear with me while I just get that done. So just to explain what I'm going to do is I'm going to basically swap the minus 45 and the plus 45 Hilbert filters around in software, and what we should see on the spectrum analyzer is those two, is it should start suppressing the upper sideband signal. So bear with me, I'm doing this all in real time, so you'll see it happening as I see it. Let me upload that to the Teensy. There, it's restarting there, and now you can see it's the upper sideband which is being suppressed. And all I did was swap over the locations of these two FIR filters in the chain here. So that basically kind of proves that that DSP filtering is working. Now, ideally, I'd like a greater degree of suppression on the unwanted sideband. It's about 26, 27 dBs of suppression. I really do need a little bit more than that. Now, one of the things that I would like to do as a follow-up as well is, again, I use a lot of cheap components, so these are all cheap components here. So you'll get slight differences in the capacitance, slight differences in the resistor values can produce a significant difference on the output. But what I'll do is I'll do it in a follow-up video, because I'll probably wrap this one, is I'll do this same experiment but with the FST3253 based mixer and see if we get any difference there. But anyway, I thought people would be interested in this. I know I've received a few requests to do a DSP based 90-degree phase shifter. And again, before I go, a big shout out to Charlie Morris and his channel. He's provided a lot of inspiration to me on all this experimentation, in particular the Iowa Hills software. Interestingly, I've been able to find sort of technical references to the Hilbert filters, but I haven't found in software any other implementation. I'm probably missing it. If you found one, I had a look through SciPy and I didn't see a similar implementation. So anyway, that's a wrap for now. Catch you later.